Oh, that are trying to catch up with each other. Microphone. There we go. It is maybe working. So when you get to that point, let me know. I'll come over and we'll see. Okay, so which one you want to do? The cars coming? I may get you to tell me the numbers and stuff. So the cars, okay, so I have a vague memory of the cars. So let's do that one first. They were both going 60. And then this guy was going first. We were supposed to figure out the distance. This guy was going first, right?
He stopped first, and it took 0.75 seconds for the second car behind him to start the acceleration.
Oh, okay. So he stopped. So was he completely stopped? Or did he decelerate?
He said he started decelerating, then 0.75 seconds later, his second car started decelerating. What's the minimum distance between the two cars so that they don't collide?
Okay. So what was his deceleration? Did they?
Um, the front car was negative 12 feet per second, and the one in the back was a negative 18 feet per second.
Okay, negative 18 feet. Okay, so this is the deceleration of these two. 0.75 seconds before he saw it. So let's focus on that one for a few minutes. And then, oops. Well, you know what? I'll just go up to the top of the board and write. How's it going over there? You getting it? Oh, okay. So we'll start with the second one, which I guess this one was A, maybe, and this one was B. Was that the case? I don't want to mix that up because then that'll. Was the first one A?
Yeah.
Okay. So let's just focus on B for a minute. And he's decelerating at 12. So that's his, well, okay. Here, I'll do it this way. Minus 12. That's his deceleration because it's plus or minus ACT squared over 2. But that was decelerating at 12. So now I just put in a box around it. So here, I know that looks weird. Okay, so his initial velocity when he started, so he started the stopwatch when he started decelerating. So his velocity here was, are they both 60 feet per second? Okay, so they're both 60. T plus now minus, T minus 6 T squared. Now what I'm going to do, and this is something that you have to kind of figure out. So it seems weird, but the instant the guy started decelerating, somebody has to have a coordinate system. Um, there's advantages and disadvantages to both using this as a frame of reference or this one. I would think, just because I don't like dealing with negative numbers, I'm going to pick this one. So in other words, here, delta t equal 0.75, just so I can remember that. And then I'm going to say minus 18 feet per second squared. How'd it go over there? Did you get it? Still the same thing. Oh, geez. Okay, so tell you what. Okay, so you're going to the site now. Well, now,
go to the side, this blackboard.
Was that blackboard? And it's still.
And he's just doing these.
Oh, well, we'll just have to wait a minute. Oh, jeez. Okay, so I'm going to use this. The instant, like someone snapped a picture, that means at that instant, he started putting his brakes on, which means that S naught is equal to dot D, which the S naught D, SBD. Oh, here, I don't want to broadcast your account, so we'll click that off. There we go. So I'll work the problem out. Okay, so you got 60, and then this D, I'll just stick it in there. Okay, so SB, so T is equal to 0. That's the instant he started putting his brakes on. Now, and I should have done this one on this side, but I can't because I don't know how far the board picks up. So I've got SA equaling to SA naught plus V naught AT. And I'm going to go ahead and put in my minus 18. And 18 divided by 2, I think, is 9. T squared. Now, here's my problem. Did it go up?
But this used to just be white when I did it. So I don't know if it's like my device or.
You know what? Maybe, so this is Firefox. So it came up here.
Mm-hmm.
So while you're still here, work on loading Firefox on that thing.
I think it's finished down.
Okay. And then just give it a shot through that. That's really bizarre. Yeah, I don't know. You know, unfortunately, people think this new education mode is good. I don't know. I'm not sure. Here, I'm going to switch to red marker. So we want to get you on this thing, so let's just keep working on it there. So you got two problems, okay? You got a stopwatch. This sounds weird, but you got a stopwatch. That's not spelled right. And then you got a ruler. Now we figured out our ruler. We're going to put our ruler here, and we're going to measure everything to the right as being positive. And then we never really have to deal with anything to the left, so I don't care about that. Stopwatch. The thing is I hit the stopwatch the minute this guy put on the brakes, but it took him a few seconds before he put his brakes on. So what I've got is until T equals to 0.75, A has no deceleration, you see. In other words, so SA is equal to SA naught, which actually, since I put the ruler right there, that term is just 0, so I don't have that. VA naught, which is actually still 60, right? They're both 60? Oh, okay. T, and then time went on, and then at 0.75 seconds, suddenly SA now becomes 60T minus 9T squared. Now, that's not necessarily true. So let's do a little plot of these two things so we can, and so this part is pretty much straight. There's nothing here that we have to deal too much with. I mean, the stopwatch started when he decelerated. We put the ruler at the other guy. I mean, it's set. There's nothing we have to do there. Over here, technology. You know, old days with just light switches. Okay, the light switches and, oh my God. Okay, so let's look at this. If we were to, I guess I'll plot S, A, and T. So what happens, time goes by, it's just a straight line. Then I can figure out at SA, what is T at SA? So if I put in, here's what I'm trying to get at, 0.75. And 60 times 0.75 is what? 60 times 3/4. What is that number? I mean, I guess I could figure it out. Did y'all figure that out? 45? Okay. So we made it to 45. Now, since the guy's decelerating quicker, let's find out some piece of information at 0.75 for this guy. Okay, so let me look at this and say this. Okay, so help me here. So look at this number and I won't pay attention to that or that. Or maybe I'll do it this way. I'll write this down. SB minus D is equal to 60 T minus 6T squared. SB minus D at 0.75. I'm just trying to get some information for myself. 60 times 3/4 minus 6 times 3/4 squared. What's that equal to? Anybody know what that's equal to? Now, geographically, plot-wise, what does this look like? If you look at it, if, I'm just saying if we put the ruler here at 0.75, he moved 41.625 feet, I guess. And by the time he moved 41.625 feet, so in other words, what happens is you see it, and then all of a sudden you see him getting closer, but you're both moving, and then he got closer. But you still move this much. He's slowing down here. And then you could basically say, I'm going to restart the problem after we move 41.65 feet. Okay, so if I restart the problem, then the problem would be restarted such that you have car A, I'll draw them as dots now, and car B, he moved in 0.75 seconds. He moved to there, which now I'm going to basically try to figure out how close they are, delta S, at 0.75. So the question is, if he moved 41 and he moved 45, we got to have a little larger distance than this. He's got to be at least 41, or he rear-ended him right then. The question is, I don't think the answer wasn't 41, was it? Okay, Because the problem is, I think, well, I guess now that I have the thing back, I can look myself. Because the problem is, okay, I'll go check his speed at that point, and we'll reform the problem. But let me give me a second here. I think I was, okay. Is that the problem? Is that how I get there? Yeah, okay, and then,
How much they stop. So if car A is going 45 feet and car B is going 41 feet, the distance just needs to make up to that 45 from the 41.
41, yeah. So he's got to be ahead, but what I want to do is make sure, do you know which problem this was?
I want to say it was towards the end.
Oh, okay. Maybe that one? No, let me go backwards. Is that it? That's it. He's saying 4.25, so is that the difference between 45 and, let's see. I don't know, because there's one other thing that really bugs me. What is 45 minus 41.625? Now the question is, there's two things you've got there. What is that number, by the way? $45 minus 41 point, what? 625. 3.376. That's where you move. So at this, it's 3.376. Now you got another issue here. And here's the way I see it. Okay, so I don't think that's the answer, but he's saying 4.25 feet. Now let's try to find out if we can logically work our way through what happens here. So if I restart the problem, at the instant that the 0.75 seconds happened, so I restart the problem, here's what I'm looking at. So at that problem, at that point, this car speed is now v is equal to v naught minus the acceleration times t. It was initially at 60. It's decreased there in 0.75. So if we restart the problem, at the instant that guy hit the brakes, then we get 12 times 0.75, 60 minus 9, or 51. So now I've got a new problem where this guy's going 51, and this guy's going 60. This guy's still decelerating at 12. This guy's decelerating at 18. Now, I'm going to define a new distance, say capital D, and I'll relate this to this. So in other words, what happened is we went, this guy saw it. He traveled 45 feet, while this one traveled 41. We'll relate this to the other in a second. So now the problem is set up to be the same. So in other words, what's this distance so they don't hit each other? So what you'll do is SA is equal to, and I'll just set the coordinate system here, 0 plus, and I'll go ahead and put the numbers in, 60 t minus, it's still the 6 t squared, and I have SB is equal to, I'll put in a capital D, but I'll relate it to the other. This time it's 51t minus 9 Oh, I've got the A's and B's backwards, so that this should be, SA should be, hang on. This should be A, this should be B. So I got B. B is decelerating, ends up with a 6 there. This one, 60 minus, and instead of 6, I have a 9. So the way I look at this, I say, well, there's two things I could do. I can, since the T's are the same, and that's actually, it should be a T right there. There's two things you can do. You can assume SA and SB will be at the same point at a certain time. And if you do, you could subtract these and find out what time they would just come into touching the bumpers, and you'd be left with a D. So let's say, assume SA is equal to SB, which means you can just subtract or add these things. You could add them if you, or here, we'll subtract them, and we'll put the minus sign here. SB minus SA, 0. They're at the same point. D minus, there's nothing apparently stuck there. 51 minus 60, that's minus 9. This minus that. Okay, so this becomes a plus now, and that gives me a plus 3t squared. I'll have to relate this capital D to this little d that he wanted. And so I didn't accomplish anything because all I'm trying to do, I think I ran myself in circles there. But if I move this to the other side, maybe I don't run myself in circles. Move this to the other side. This becomes 9t minus 3t squared. So if I look at this, t versus d, okay, I start with this. I have a slope, but then, so if I put in t is equal 0, wait a minute, that's not going to get me anywhere because t is equal 0. I've run myself around in a circle there. Okay, let's think about that. A and B. See, so this problem isn't that easy. Did anybody get it? Did y'all work around and get it? So let's think about this. Okay, so I want SA and SB to be the same. I still got it parametric. The other thing I could do is I could set these equal to each other, but I get the same exact equation. Let's stare and think about this for a minute. That would give me D as a function of time. And so I could plot it. But the problem is the plot that I'm coming up with is such that D, when I put in t is equal 0, is, so I'm forgetting a constant term here. So if I put my coordinate system here, but we're looking for the maximum D. You don't suppose we take the derivative of that thing and set it equals 0. Okay, so if I plot this thing, see this doesn't make sense. What I really need to do is I need to write it like this, okay? So here's what I need to do. SA, I'll take SA minus SB, and that'll be equal to the distance between them. And then what I'll do is I'll take this minus that, which I'll end up with the same equation, but this time it'll make a little bit better sense. I've taken the SB, so what I'm going to do is take SB minus SA, look at the distance, and I'll say D, and I'll say it's still this minus that, minus 9T, this minus that becomes plus 3T squared. So now the distance between them looks like that. Okay, so the distance between them, the minute you hit T is equal to 0, you're at a distance there. You've got, you know what, I might just plot this just to be, I think I just hit it. There it goes. Oh, here. So, if I were to plot this thing, let's just pick 0, I'd get this. If I pick T is equal to 1, that'd be 9 minus 3, so I would be, we don't know what this distance is, but you would take that distance, and at 1 second, you would be, 9 minus 3 would be 9 is 6, so you would be 6 below it. So maybe 6 below that. You go to T is equal to 2, then it become, so what I really want to do, I could take a derivative, or I could look and see how this part of the curve looks. So here's what I mean. This sounds weird, but I'm going to put in just a guess for the value of D. D is equal to 10, say. So that's how far they're apart. And I'll go back and change that. So now I'll say T, it can't be more than 5 seconds. So we'll say there's my time. And then I'll say my distance is equal to my D minus, okay, that's too far over there, minus 9T plus 3T squared, minus 9T where times T plus 3 times T squared, and I get a bunch of values, but I want to plot distance. Now I want to plot the x and the x-axis to be time. Okay, so there's what I get. So if it occurred, if this situation occurred, you stayed 5 feet away from him, or maybe 4. So if I keep moving this down until I hit this point, turns out I could take the derivative. It looks to me like it's at 1.5 seconds. But, I mean, technically I think that's probably what he wanted you to do. But let's see if I can do, I'm going to do this. I'm going to zoom in. I don't know. To me, it looks like about 1.5 seconds. So at about 1.5 seconds, that was a really poor way of getting around taking a derivative. So at 1.5 seconds, after the 0.75, they become the closest, and then the second car slows down faster. So at T equals to 1.5 in the second phase, then they become the closest. Now, if you wanted to, if we want to relate this back, we know that 0.75 seconds happens, and then 1.5 seconds happen, and that's when they're almost hitting each other. So you could do this. You could go back here, put in, I don't know, let's see, 1.5 more seconds would be, this is 1.5, so what is that, 2.25? And then over here, it would be the same thing, 2.25. Maybe, anyway, so SB at 2.25, let me make sure, 0.75 plus 0.75 plus 1.5, yeah, 2.25. So according to this, if I've got that, D plus 60, 2.25 minus 6, 2.25 squared, and then I go over here, and that sounds weird, but I already moved 45, and now I'm going 1.5 seconds more, which means SA would have already gone 45, and then plus 60. Now the delta T during this period is 1.5 minus 9 times 1.5 squared. Now if I enter all this, okay, you have to give me a minute. 1.5 times 1.5 times 9. And what I'm going to do, I'll do it in little parts. 20.25. And then 60 times 0.5. 90 plus 45. 135. 135. I still have that on. Minus 20.25. So he's moved 114.75. So during that period, he went with no deceleration, moved 45 feet, hit the deceleration. When he hit that deceleration, during that period, it's 1.5 seconds. Then he got to 114. So if you look at SB at 2.25, and then you enter this, okay, I lost my, okay, here we go. 2.25 times 2.25 times 6, this is minus 30.375, and then 60 times 2.25, 135. Now I can, since that's still on the calculator, I can subtract 30.375, 104.625, and now if I subtract the two, I get a different number than what he gets. I get 10.125. So I'm going to go back and look at this because I get a different number than what he gets, unless, oh, he's got that at 8. So I just worked it in. Oh gosh. Okay. You know what I'm going to do? I'm going to take a picture of the board and I'm going to work this with one set of numbers. Okay.
What are you supposed to do after you metaphorically restart the problem?
You mean redo this?
No.
Oh.
Can you
Okay.
set the initial velocities once both of them start decelerating? What's the next step? Do you set them equal to each other and then take the derivative?
What I was trying to do, okay, right here, is I was trying to say, hey, there's going to be a period where this guy's decelerating, but he's already going 60, and so he's still getting closer to him, but then he's going to slow down more. So that was what I was trying to do. I was trying to get this plot to find out what's the closest they get. But it turns out, as I looked at that plot, it's 1.5 seconds. So the second he hit his blade, 1.5 seconds, he still was getting closer, and then he slowed down. He was out braking him. So they got to. So did you get in? Did you? Okay. Oh, but it worked on Chrome. How bizarre. I'm sorry about that. You know what I'm going to do in this first assignment? I'm going to shove the due date back. There's some things that it allows me to do, some things that it doesn't. On this first one, I'm going to shove it back. And so just keep working them. I'll shove it back. I'll widen that test on Friday to include all the way through Sunday. And so that gives you a little extra time. So just keep working on it. So your grade, you may post a grade today, and you may go back, and when you look at it, it's going to increase because of that deduction. So just keep working on it. And so does that, okay, so does that make sense what I was saying?
I don't know. It makes sense for the plot, but I don't know how you got the plot. What equation did you use?
Well, what I did was I realized that there's a D. It's a different D than the previous D. And I was like, okay, at a certain point, there's going to be a distance between these guys. So then I subtracted these two. And I was like, I can't do this. I got to plot it. Because, you may normally want to take a derivative to find out the minimum. So let me know if there's any more problems with that.
Okay.
And so,
Okay.
okay.
Because if I take a derivative of that without the D in it, the D's moved to the other side.
Uh-huh. Well, it's constant anyway, so it goes away.
Yeah.
So if I take a derivative of that mass,
4.5 was negative 4.12.
oh, well, wait.
Not 1.5.
Right, and so okay, so let's take a derivative of that thing. Okay, so I'd get a minus 9, and then,
Plus 60.
yeah, and so, so if you set that equals 0, move that to the other side, 6t equals to 9, t equal to 9/6. Wait a minute, is that 1.5? No, that's not 1.5. Wait, 3 times 3. Oh, yeah, it is. So it's 1.5 seconds. So at 1.5 seconds, after they break, they got the closest, and then this guy broke them or whatever.
So you take the derivative of these equations subtracted from each other.
Yeah.
And then solve for t, you get 1.5 seconds, which means that A is the closest to B at 1.5 seconds.
Right. So what happened is the stopwatch started. We went 0.75. We restarted it 1.5 seconds after that. So then what I did is I said, okay, so I can use this total time, 2.25, together in the first equation for B, because that's where, so I used the 2.25 there. Then I realized, okay, for car A, during this period, I went 45 feet. And then I got a new equation, which is the part of the deceleration, and that's where I included the 1.5.
So you just add those together and then take that difference.
Right.
And that will be
And that'll be
how far they need to
be
be.
apart, yeah.
Okay.
Does that make sense?
That does make sense.
It is, when you really look at it, you look at it and you're like, oh, that should be an easy problem. And then you start thinking,
Yeah.
no, it's not.
That's what I did as well. As I went, oh, okay, sure. And then it didn't turn out
Yeah.
how I wanted it to.
But it requires, and that, I guess that's what really makes me think this thing is actually a pretty good idea, because when you start seeing stuff like that, it makes you think about a lot of this, and it's like, oh, wait a minute, okay. So That's not that easy. I mean, the equations are easy, but the thinking of where you're starting your stopwatch, where you're starting a ruler, where you're doing that stuff, that's not easy stuff. So,
Do you mind if we go over the equation, the problem where it's 2 over s equals the acceleration?
yeah. Well, you know what I'll do? I will shove the due date all the way to Friday, and I'll I'll come work those two on Wednesday. How about that?
Sounds good.
Okay. Keep working at it, though.
Okay. You have a nice day.
You too. Slow, slow, slow. We go slow. I guess that's okay.
It's on the third floor, so it doesn't take me long to come down.
Yeah, let me get out of your way there. I'm sorry I ran over.
You're okay.
Okay, wait a minute. I got to figure out how to get out of all this mess. Oh, and I got to stop the stream. The other day, let's see, oh, there is audio. The other day, I've done